Okay, so today we're going to talk about the derivatives of exponential functions, e to the x in particular. We're going to leave other bases to after we talk about logarithms. And you'll see there's going to be a relationship between exponential functions that have differing bases simply by making an alteration or a modification of the exponent and the coefficient. So if we deal with just e to the x, we'll get a good foundation on that particular one. We'll talk about logarithms next, and then we'll loop back and see the derivatives and integrals for exponential functions that have a base other than e. Okay, so let's just review derivatives a little bit. I know some of you are fresh out of Math 13, so you know this. The rest of you took Math 13 in the fall, so maybe you forgot a couple rules, but let me briefly go over them, and hopefully this will stir out the cobwebs. In fact, I'll show them all. We have, of course, the power rule, where if we have x to the n, we get the derivative of that. It's just nx to the n minus 1. So if you have like x cubed, the derivative of that is going to be 3x squared. If we have the product of two functions and we want to take the derivative, unlike limits where we can just multiply the limits together, we have to use the product rule. So we take the derivative of the first function times the second function, and then we take the first function multiplied by the derivative of the second function. We have a quotient rule that has kind of the similar pattern where we have f prime, g, f, and g prime. The difference is that we're taking the difference there and we're dividing by the function g squared. We have the chain rule, which when we have a composite function, we take the derivative of the outer function, leaving the inner function alone, and then we multiply it by the derivative of the inner function. And then we have a generalization of the power rule where we combine it with the chain rule, where if we have some function u to the n, the derivative of this is the power rule, mu to the n minus 1, and then times the derivative of u. So this is both the power rule and the chain rule. I don't really care if you know the names of these, but it's sometimes just handy to be able to talk about them. I do expect you to know the rules, and hopefully, since you've all passed the Math 13 Gateway, you're all expert at this, or at least can do it with a reasonable sense of reliability. Let me say it that way. I'll be kinder that way, right? Okay, so let's get into the derivative of e to the x. Notice back here, none of these things had to do with exponential functions. This is a power function. There's nothing explicitly that says anything about an exponential function. So if we try to take the derivative of e to the x, there's a lot of different ways to prove this, and we'll prove this in a couple different ways as the semester goes along. Or what we can do is we can define it as the derivative of e to the x equals e to the x, and then we get all the other definitions of e to the x as a result of that. So this is just the handiest, probably the simplest derivative I can think of. I mean, it's simpler than taking the derivative of a constant where you know that's going to be a 0. This derivative is itself. Okay, so we rarely have just e to the x. We have e to the u, where u is some function in x. So we still need to apply the chain rule, right? Where we say the derivative of e to the u is e to the u, and then we multiply by the derivative of u with respect to x. So a few examples. If we have e to the 2x, finding the derivative of that with respect to x is just going to be e to the 2x multiplied by the derivative of 2x, which is just 2, so I put the coefficient in front. And feel free to do that. That's a more standard way to write it than to write it at the end like you frequently do with the chain rule. E to the negative x, we keep the e to the negative x, and then we multiply by the derivative of negative x, which is negative 1, so the derivative here is negative e to the negative x. So if we have something that looks like this, where we have e to the x squared times 3x squared plus 1 squared, A little bit more difficult, but you can compartmentalize it. You see, it's a product, so we're going to use the product rule, and we're just going to apply the rules of differentiation now that we know e to the x as well, considering the chain rule. Okay, so the first term, we'll take the derivative of e to the x squared, and so we keep the e to the x, take the derivative of x squared to 2x, and then we write the second function unchanged. And then the second part of this is that we take e to the x squared and we take the derivative of this, and this calls for the chain rule as well. So we have 2 as the coefficient. We subtract 1 from 2, that's the new exponent, to get just a 1. And then we have 3x squared plus 1, so we take the derivative of that, since that's the inner function, as 6x. And then we probably just need to write this a little bit more compactly, collecting the coefficients. Now, I know on the gateways it doesn't care if you go beyond here, but I think for the purposes of our written work, at minimum, I'd like you to collect up similar terms, especially coefficients. So, you know, this is a little bit more standard of a way to write it than the one preceding it. So this 12x times e to the x squared, that's a easily readable expression. Any questions on this particular one? And this is almost as complicated as it gets, because you already know everything that has to do with algebraic functions. So if we add in e to the x, we just remember to correctly apply the chain rule when we're taking the derivative of that particular function. Okay, so you should try and find a few of these. And in fact, this is going to be most of our activity regarding this. So I'm going to write them all up here and circulate around to seeing how you're doing. A couple pointers here. When we have things in the denominator, remember we can put a negative exponent to that and bring it up into the numerator if you prefer the product rule over the chain rule. You have things like this where you can simplify these by simplifying the exponents, okay? I won't tell you exactly how to do that, but we'll see it in the answer. And I think the rest is fairly self-explanatory. So go for it, and we'll see how you do on it.